Hello and welcome to the Big Data Platforms lecture number 7. First of all, some announcements. Remember that today is the last day to submit the home assignment number 1. Um, it seems that quite a few of you have already done so, good, good for you guys. The home assignment 2 has now been also out for a week. And now just this morning we released the home assignment number 3. So the home assignment number 3 is now available for you to work on. Um, so that's the basic announcements. We're uh, closer to the end of the course as far as the lectures go. So the last lecture with quizzes is lecture 10. And then lecture 11 will be more about what kind of research do we do in our research group. And that will not have attached quizzes to it. Today we're going to talk about cloud-based data stores, and we're going to talk about Bloom filters as I promised last time around. Let's see, we might have a slightly less material to cover today than in some of the other lectures, so let's see if we are able to finish early today. Okay, let's get started with lecture 7. And remember, at any point in time, you can type your questions in the chat. I'll be monitoring the chat at all times, and I will answer as quickly as I notice your question over there. Okay, so let's get started. So NoSQL databases or cloud data stores. So quite often the term cloud data store is used for database systems developed for the cloud, as they often do not fully support all the features of traditional relational databases or relational database management systems, RDBMS. Another term often used is NoSQL databases, as the original systems didn't support SQL. However, some SQL support is getting added also to cloud data stores, so the term is getting outdated quite fast. And these cloud data stores are not a single kind of thing. Rather, they are a very large collection of different kinds of data stores or databases. And thus, they can be grouped by many different characteristics. I'm using here as a background material a paper by Rick Cato, Scalable SQL and NoSQL Data Stores. It's already an old paper, but it has a nice kind of grouping of data stores that I found quite useful. So I've kept using that in these slides. Okay. So the Cathwood paper lists some key features that many of these new cloud data stores include. And you must understand also that no single system contains all of these features. The main thing that almost all of these systems have is that you want to have the ability to horizontally scale simple operation throughput over many servers. So cloud data stores were originally developed for let's say internet scale services backends. So if you have like let's say a video service like for example Netflix, you need a data store that's able to cope with the millions and millions of clients you have. And in order to do so, you want a data store that is able to scale to hundreds, if not thousands of servers. And these simple operations are things like, okay, users logging into the system, users finding, for example, what movies they can watch and things like that. Users updating their preferences. So the simple operations are quite often required to implement websites, and and these cloud data stores were built to scale up to really massive user amounts. Then the second property that many of these systems have is that they have ability to automatically replicate and to distribute data over many servers. When you have a lot of servers, those servers will have a lot of hard disks. And because of that, you will also have a lot of broken hard disks in your servers. And if you have a large number of servers, you will also have broken servers in your database cluster. So you want the database system to automatically kind of replicate data to several servers so that if you lose a server or a hard disk in a server, that data is available in other servers as well. So no harm done if you lose some particular server or its hard disks. Also, you want to partition or shard the data on many servers. So what does sharding mean? Well, it means that you want to be able to distribute the load as evenly as possible. And you want to be able to split the database into smaller parts such that not every database server has to have all of the database in its hard disks and serve that, but only some part of it. So sharding means kind of splitting the database into smaller parts, and then each one of the servers serving its part of it. But because of replication, then you typically have several servers that are serving a particular shard in these systems. Then originally, these systems had a simple call level interface or protocol instead of supporting SQL. And from there, the term NoSQL came from. So they didn't have full SQL support originally. However, newer systems are adding more and more SQL support to them. So the NoSQL part of the naming is no longer valid for them. And some of those systems are calling themselves new SQL as kind of new database systems that also support SQL. Okay, so that's kind of three properties. So horizontally scaling, so using lots of servers, then sharding, so being able to split the database into parts and the subparts being served by subsets of servers, and then typically having not full SQL support. That was what was there initially. Other features that are also associated with these cloud-based data stores are the following. Quite often, many of these systems do not have a full ACID transactions in them. Instead, people are using weaker concurrency models, for example, having AP systems that are available and partition tolerant instead. One of the interesting features many systems have is that they are using the main memory, so RAM, of the servers more efficiently than traditional relational databases. And quite often they also have features like distributed indexes in them. Some of the systems also have the ability to dynamically add attributes to data records. So there's no fixed data schema. So unlike in relational database systems where each one of the tables has a particular number of columns and each one of the columns has a fixed data type description, in many of the cloud data stores, you can have a different number of columns on each row of the database, if you like. And also in many of the systems, you can also dynamically have different types of data in different columns. So, this is of course similar to having like dynamic typing in programming languages instead of static typing. So the relational databases would be like statically typed programming languages as an analogy, And these cloud data stores, or many of them, are more like dynamically typed programming languages, where um, kind of each one of the data items themselves carry the type. What type are they? Okay, so let's move forward. Um, so here's then other groupings. And one of the ones that was there in the very beginning are key value stores. And on a high level, you can think of these as being kind of glorified hash tables, glorified distributed hash tables. So key value stores, some examples are Redis, Riak, and Cassandra. Cassandra is a difficult one because it has a lot of different kinds of features. So, but Cassandra is partially matching also this key value store kind of feature set. On the academic side, there's a not widely used system called Scalaris. That's also a key value store. And the idea here is that these are databases where we use a unique primary key to access the data item that's originally usually was a binary blob, so meaning just a bunch of binary data. So you would basically have a hash table-like interface. You could access with a key a particular item in a hash table, so in the key value store, and you would get back the data item, let's say 1 kilobyte of data or whatever you stored there. And typically these systems then um, when they got developed further, then they got away from binary blobs and started adding support for structured data. So having data types and whatnot. So yeah, and then the underlying technology on which these were made were actually similar to peer-to-peer networks. So peer-to-peer technologies such as distributed hash tables and a technique called consistent hashing that will go into in a future lecture um, were used to shard data, so to split the data across the different servers and to allow elastic addition and removal of servers. So the basic idea here is that if you have a database that's serving, for example, a website, and the website has a very spiky load. For example, it could be that it's a game server and it has a lot of players in the evening hours. Then you might want to add a lot of database servers to the cluster, to the database cluster during evening hours. But then during, let's say, during the working hours, you might get away with less servers. And quite often, these key value stores allow you to remove and add servers into a running database cluster. And with that, you can save money as far as the number of rented virtual machines is concerned. So if you're running in a cloud on let's say on popular days, you can rent more virtual machines to get good performance. But then once you have a slower pace, then you can also kind of get rid of the servers and still have the users not notice it, except that yeah, you're running the database on physically less servers. And this is very interesting, especially for people who have very varying database load, and could be a real cost-saving measure because you don't have to kind of book in advance the database to handle the top load. You can basically add servers as needed, and basically the customers of that database will not know this necessarily. Okay, so that's key value stores. Um, some other things that these key value stores have is that many systems use, or let's say, maybe not many, some systems only use main memory to store data, and thus are basically cache replacements. For example, Redis is quite often used in a mode where it's basically just a cache. So it's a massive distributed hash table that's working as a cache for an underlying other database system. Um, Other systems also persist data to the disk. For example, Cassandra is such a system and thus can be used as persistent database replacements. Now, because these systems are basically used for interactive services quite often, then most systems are AP just to get better latency. There are some exceptions. So the academic system Scalaris actually is a CP system, but that's more of an exception to the rule. So Scalaris supports local row level transactions while still doing replication. But most systems in here are AP systems. So if you remember our talk about the CAP theorem, these systems will potentially cause kind of data inconsistency issues if you have concurrent updates to the same data items while the servers are not able to talk to each other. But the idea is that these systems will try to keep the database up and running all the time, um, just to get better kind of customer experience in them. Now, Cassandra is hard to categorize as a key as a kind of cloud data store, as it uses a distributed hash table. So it's using the same technology as these other key value stores. It is an AP system, so it prefers to be available instead of insisting on being consistent, but it has a very rich data model. So basically, it has a data model that allows very structured data. So looking at the data model, it's kind of way ahead of many of the other key value stores in features. Okay, that's what I have for key value stores. Any questions about key value stores at this point? Okay, let's move forward. You can type in any questions at any point. Let me remind that. Okay, now the next class of systems is called document stores. And the system you might be most familiar with from here is MongoDB. Um, these are typically used for storing structured documents, for example, XML documents. They typically do not support transactions or ACID semantics. Okay, there's a question from Ayman. PostgreSQL also supports now NoSQL. Can we consider it instead of other NoSQL databases? What do you mean Postgres supporting NoSQL? What are you referring to? I noticed, okay, I did a quick Google. It seems there's some NoSQL features in Postgres. I haven't taken a look. I will definitely take a look at this, but I won't be able to do it right now. Okay, so thanks for the pointer. I didn't know that. I'll definitely take a look. Okay. All right. then yeah, coming back to document stores. So Mongo um, is one of these typical systems, and they typically do not support transactions or ACID semantics. So so when you insert data in MongoDB, you might want to index that data by many different uh, columns, basically, of the data you've inserted. But in Mongo, these indexes are basically updated in a delayed fashion. So not all of the data that you insert is immediately visible through all the other kind of indices. So it might be visible through the one of the indices, but not all of them. And because of this, it's not really a fully consistent and partition tolerant system. It's kind of trying to do things on a best effort basis. So typically they do not support full transactions or full ACID semantics. Uh, Mongo and Co usually allow very flexible indexing, as we talked about, and that's super convenient. However, the main focus of this class of systems is on programmer productivity, not ultimate data store scalability. So, so that's I would say if you use Mongo and Co, you're not planning to implement a Netflix scale database system. Um, if you have some smaller systems that have small loads, Mongo might do just well. However, I'm a bit worried of the Mongo let's say documentation heavily implying it's a CP system while it isn't. So I'm a bit wary of Mongo on its own as well. So I would say Mongo for small projects, but please don't implement something like a banking system on top of Mongo because it's not ACID really. So yeah, I would say for small projects, but not for really kind of this internet scale, very large systems. I wouldn't suggest Mongo or other document stores. Then we have the next group, which is extensible record stores. And it is called also in the Cattle paper Bigtable clones. And Bigtable is a database system designed by Google to implement many of their services. For example, Google Maps used to be based on Bigtable a long time. Also, Facebook messaging used to be based on the Apache HBase, which is a Bigtable clone for a long time. Now they moved off of it. Um, so these are actually interesting systems because the Google Bigtable paper gave a new database design approach that other systems have emulated. And Bigtable is based on a write optimized design. So the read performance is sacrificed to obtain more write performance. And why is that? Well, typically, Bigtable is used as a backend system with a caching layer in front of it. And if you have a caching layer in front of a database, then that caching layer is typically getting most of the read workload. And after that, typically your bottleneck is actually the writes. So if basically all the reads are being handled by a caching layer, then your database is mostly kind of doing the right side. And Bigtable is a write optimized design where you again sacrifice read performance to obtain more write performance. We'll see in future lectures how that's implemented, but it's an interesting trade-off. The other part is that it is a CP system, so Bigtable and HBase and others listed here, um, except for Cassandra, are consistent and partition tolerant systems. So they insist on the data being consistent across all the replicas of the database, and will basically put the database offline, or at least in a read-only mode if you are not able to communicate between the different database servers in a database cluster. And because of this, also quite often these systems are run inside a single data center just to minimize the possibility of network breakage between the database servers. And yeah, so it's basically a way to do CP database systems at a really massive scale. They are doing automatic sharding on primary key. So basically, you can think of it in this way that if you have your database table, you sort your data by the primary key, and then you split in, I think it's by default in Bigtable, something like 1 GB chunks. So the first gigabyte is one shard, the second gigabyte of the database table is another shard, and each one of the shards then goes to a different server to be served, or a different group of servers to be served. So automatic sharding on a primary key. There's also a flexible data model. We'll see more details later, but it's basically you can have different rows of the database table having different number of columns with different data types in them. Okay, there's a question from Frank. Can we consider MongoDB for e-commerce application? Will it be easy to manage transactions and product stock in our database, thinking to ACID properties? Um, uh, okay, my 2 cents on that is I wouldn't use Mongo for anything that has to do with money or with anything financial, because Mongo is not a fully CP design, and there have been bugs found in Mongo earlier on. Uh, I'll have a pointer later on that have found bugs in Mongo data consistency. So for if I would be using Mongo, I would be using it as like a front end to another system that is fully CP, so that I have the let's say the financial transactions done in a system that truly is a CP system, and then using a Mongo-based system as potentially a cache or like an AP caching layer on top of the CP system. So that's my 2 cents to you, Frank. If you read Mongo documentation, it will say how it's fully consistent and everything, but don't believe everything you find in vendor documentation. So that's my 2 cents. Did that help? Okay, Frank. Okay, there's Kai. Are there optimization approaches to the automatic sharding? Using a sorted primary key seems rather naive approach. Um, in a way, yes. The the sharding in Bigtable is done by the sorted primary key. However, people are really kind of designing their primary keys in a way that implements the sharding. So you can, for example, if you're storing websites, for example, in HBase or Bigtable, then if you store your websites in the order of the URL, so let's say www.cnn.com, and then you might have www.2.cnn.com and whatnot, or then those two might be maybe not close to each other because there's a lot of wwws in the primary key order. However, if you store the URLs in reverse order, so you store them in the order com.cnn.www, then all the things that are on the same site are then next to each other in the sharded primary key order. So by kind of reinventing your primary key and the sort order on your primary key, you can do more intelligent sharding. So that's the trickery in there. Okay, thanks for a super good question. Okay, there's a question from Ayman. What is a truly CP system? So we talked about consistency and partition tolerance last time around, but basically um, a CP system is something that is, like I would say, the NoSQL version of ACID. So a database system that is not going to be inconsistent when we have network outages. While the AP systems are such that they will always allow writes, even if the database servers are not able to talk to each other, which can result in a state of the database where different servers in the database think some rows of the database have different values. So CP is basically, I would say, the NoSQL version of ACID. And with CP, I would be willing to do things like financial transactions because I will keep my data consistent. So I will not lose money. I will not duplicate money. With AP, if I do financial transactions with AP, I can always lose money or duplicate money by accident in cases where there's network outages. So, Ayman, I hope that answered your question. Okay, let's move forward. So these guys, extensible record stores, these are the closest ones to ACID, as I was talking about. And then you have also the kind of relational database equivalent. So these are called scalable relational systems, aka distributed, I would say, relational databases. There's a couple of examples. There's, for example, MySQL cluster, which is a different code base than MySQL, but it's coming from the MySQL company. So because of this, it is also called MySQL, even though it's a completely different code base from the basic MySQL. MySQL cluster is used, for example, for some mobile phone networks, visitor location registers that to figure out, for example, which SIMs in mobile phones have which subscribers in them, etc., etc. So it's used in the network kind of mobile phone networks, for example. Then there's VaultDB, and then there's things like Oracle Real Application Cluster or Oracle RAC, which is a database system where which you can buy from Oracle. And basically, Oracle will provide both a cluster of servers and the software to be run on it. And basically, these are relational databases that are running on a number of database servers. Quite often, automatic replication of data to several servers is supported in this case. Usually now we get full SQL database access and full support for ACID transactions. Now, even though you can do SQL queries, it doesn't mean SQL queries are fast, especially if you do joins that span multiple database servers, or if you do global transactions that modify all of the servers in the cluster, then you might not get a good performance, even though you're able to do them. And one of the things in here is that these things do not scale to very large database server clusters, like 100 plus database servers. But there's no inherent reason why this couldn't be done. But things like, for example, HBase and Bigtable, they are routinely run on 100 plus server database clusters. So those systems, so these extensible record stores we had on the previous slide, actually do scale to very high database server cluster server numbers. Okay. Now, there's a terminology that's called eventual consistency. So if you find a database that's saying that it's eventually consistent, it is basically a term that was popularized by the authors of Amazon Dynamo, which is a data store that is an AP system that is available and partition tolerant. So this eventually consistent doesn't mean that it's consistent. It doesn't mean it's a CP system. It's an AP system. The eventually consistent in here, this means that when you query data from the database and there are conflicting versions of it, the database system will tell you to merge those and say, okay, here are the conflicting versions of this row in the database. Please merge them. And if you do the merge on your own, using whatever application-specific technique you have available, then you can write back to the database a single value that will override all the existing kind of conflicting versions, and then it is kind of consistent. So this is what they say, eventually consistent. That yeah, by doing these kind of user kind of user-based merges of conflicts, you can get the database back to a consistent state. And now also you might run into terminology called base, basically available soft state eventually consistent. And it's basically a synonym for the same approach. So eventually consistent and base and AP are basically the same thing. They are just different kind of, I would say, even marketing names for the same thing. So basically, these are all data stores that value availability over data consistency. So they are AP systems. And quite often, databases that have eventual consistency support some automatic way also to merge some of the inconsistencies. And these techniques include things like version numbering, which might be, for example, always updating the value of a column in a database table each time it's updated. And then if you see an older version, then you know that the newer version is surely the right value. However, if you have, let's say, multiple servers updating the same column at the same time, then you will have version numbers that look something like, okay, version 1 has updated this the fifth time, and server, let's say, another server has also updated the fifth time. So you get versions that are incomparable. So the version numbering doesn't help there. Other things people use are timestamps. So using timestamps where kind of newer modifications always override older modifications if you don't. So if you don't provide a way to merge conflicts, the system will just overwrite old modifications with new modifications based on the timestamp. And then we have this problem, as we talked earlier, where if you are selling tickets in Helsinki and Stockholm and you sell a lot of tickets in the morning in Helsinki and one ticket in the afternoon in Stockholm, then the Stockholm update is newer and then it will override all the Helsinki updates. So also timestamps are potentially dangerous. And timestamps are actually the default mode of merging conflicts in many systems, including Cassandra. One exception to the rule is something called commutative replicated data types, or CRDTs, which are a technique for merging updates that work for some types of data. For example, you can update counters in a way that is actually sound in the sense that you are able to kind of how would I say, you're able to get to the final state that is actually correct. And why is that? Well, for counters, for example, it doesn't matter in which order you update counter or in which order you apply counter updates. So if server 1 updates a counter 5 times and the server 2 updates the counter 4 times, then no matter you update them first 5 times and then 4 times, or first 4 times and then 5 times, you will always increment the counter 9 times. And because of this, you can basically just record all the updates you need to a counter and then apply them in random order, and you get to the same final state in any one of those. And with that kind of insight, you can update some data types, for example, counters. Now, example systems of eventually consistent systems are Dynamo, which we'll talk more in detail in upcoming lectures. And we'll also cover Riak and especially Cassandra. Cassandra is fairly widely used in the field. For example, Netflix is using Cassandra heavily. Okay, now any questions about that so far? Okay, so there's a question: do we need to use Docker image for all the assignments? Yeah, the home assignments are to be done with Docker images. That's the same for all the assignment routes. Okay, let's move forward. So here's the so-called flame war that has been going on. And here's the relational database supporters view. The relational database supporters say, okay, relational databases can do everything that these scalable cloud data stores can do with similar scalability when used properly. I don't fully buy that argument because we don't see relational database clusters that are, let's say, 100 plus servers in size that are used in similar fashion. We do say kind of manually splitting the database into 100 shards and then using those 100 shards, each being served by a single relational database. That's what I see, but not like automatic sharding. That I don't see at that scale. Then the next point is SQL is convenient, expressive declarative query language. I fully agree with that. Then the next one is relational database management systems having 30 years of engineering experience have 30 years of engineering experience put into them and are highly tuned. I kind of agree with that. There's the amount of low-level tweaking that has gone into relational databases is quite impressive. Then the next one, there are a very large number of specialized relational database management systems for various application domains, interactive versus analytics, RAM versus disk-based data, etc., etc. Yes, there are. Not all of them are in wide use. But yes, there are some relational database systems that have different strengths. So that's true. Then the last point, standardization around relational schema and SQL brings benefits in design and training where the same set of skills can effectively be employed with another relational database management system. And I fully agree with that. So if you know MySQL, it's really easy to learn um, PostgreSQL and or Postgres, and then while on the cloud side, if you know Redis, it's quite different from let's say HBase or Cassandra. So yeah, having kind of the same kind of API is really beneficial, especially for training purposes. Then here's the other part of the framework. So the cloud data store kind of supporters side. Um, then there's the point that relational database management systems have not demonstrated the scalability matching um, systems like Bigtable, for example. And I actually agree with that one. Then the next one says primary key lookup is easy to understand, more easy to understand than SQL, and thus enables a much lower learning curve. Um, I I don't fully agree with that. Of course, if the only thing you need is a hash table, then let's say using a key value store is of course pretty straightforward. But as soon as you start to do any queries that involve several database tables, then key value stores can be actually a very painful place to be. Okay, then the next one, relational database management systems for data schema on applications unnecessarily. So that's the question of, okay, do I want statically typed or dynamically typed databases? So it's up to the designer. I would say either one depends on your goals. Then the next one is SQL makes it too easy to write expensive queries by accident, such as complicated joins involving many tables and several servers. If these features are removed from the query language, the complexity of query evaluation becomes obvious to the programmer. Excuse me. For this, I kind of semi-agree and then I don't. So it is true that with SQL you can write truly kind of complicated queries really easily, and of course, if you don't think about it, you don't have the right indexes and whatnot. Those queries might take a long time to actually be evaluated by the database system. However, if you don't have those features, then it can take a lot of programming to implement the same queries with, let's say, something like a key value store. So yeah, it's I don't really agree with this. Okay, then the last point, which is a bit like punching under the belt or something. Relational database systems have become dinosaurs in their 30 years rule of database market, and thus the hardware assumptions on which they have been built are obsolete. This is an interesting quote. and part of it is true. The hard disks haven't sped up a lot in the last 30 years in relational term or relative terms. However, we've gotten huge amounts of main memory, for example. So the NoSQL databases or cloud data stores are heavily using main memory to do caching. That many of the SQL-based systems are not really kind of using that much of. So typically, you then need a separate cache in addition to the database system. While on the NoSQL side, some of the systems might do the caching on their own, and you don't necessarily need a caching layer on top of the database. Some other things are, for example, the processor speeds have increased massively in the last 30 years. So you can do a lot of things that basically were not possible nowadays because you can spend a lot more CPU cycles to do your queries. And however, there's some truth to also things like, okay, now we have actually flash memory, and the speed of hard disks, let's say comparatively to CPUs, is 30 years ago is roughly the same as the speed of CPUs to flash memory these days. So actually, because of this, some of the kind of hardware assumptions are not that far off if we just replace hard disks with flash memory. Okay, so there's a question from Kai. Isn't it possible to prevent expensive queries on the compiler level? That's a good question. Yeah, but I don't see it kind of heavily implemented in database query systems. So I would say the database query performance is a bit of a black magic art. So of course you could try to restrict the SQL queries you write, but I don't see any systems taking that route. So in theory, yes, you could do it, but in practice, I don't see any systems that have implemented such a restriction. Um, then there are also things like, for example, the performance of some database queries might be quite different on different data. For example, um, many of the optimizations in database query systems, for example, for doing joins, are based on things like, okay, is one of the tables, let's say, that we're joining less than 1 MB in size? And if it is, then run join algorithm A. And then let's say your database table grows and suddenly it's slightly over 1 MB in size. And then suddenly your query optimizer switches over to join algorithm B, that might be much slower. So depending on what exactly you have in your database tables, you get a different query. And that might surprise people because they are not expecting their queries runtimes to change overnight because database tables grew. Okay, there's another question from Kai. So he's thinking about replacing the joins with nested queries, which is often possible. Of course, the SQL database query optimizers do a lot of good stuff. Yeah, so quite often they can let's say um, they can do things that a programmer wouldn't think of if they would do the query kind of on hand by hand. So there's a lot of good work put into SQL query optimizers that you don't get benefit of if you are not using it and you're writing your own queries straight away. So I agree with that part. Yeah. Okay. Cool. Now, so I would say this is kind of the state of the flame war. Um, so here's some future speculation on my part, which you may or may not kind of agree with. So I think long-running serializable global transactions, so something where you want to update every server in your database cluster, they are very hard to implement efficiently. For scalability, they should be avoided at all costs. Just because you can do a database transaction that updates all the possible servers in your cluster, you shouldn't do it. There's a couple of counterexamples where people have actually allowed that. For example, there's systems called Google Percolator and Google Cloud Spanner that allow you to do transactions that span across a very large database cluster where the database servers might be on different continents even. However, that doesn't mean that those database queries are cheap. Uh, Quite the opposite. I think those database queries will be very expensive, and the database admins will not like you if you run such queries. Just because you can do expensive queries doesn't mean you should do those. Um, then the requirements of low latency and high availability make AP solutions quite attractive, but they're more difficult to use for the programmer because you need to provide an application-specific data inconsistency recovery routine. So CP systems are easier to program against. I'm of the opinion that the time of one size fits all, where relational databases was solution to all data store problems, or relational database was the solution to all database problems, has passed, and the scalable cloud data stores are here to stay. But they will also evolve. Then ACID transactions are needed, for example, for financial transactions, and their traditional relational databases will be dominant. Um, and then if you need to do, let's say, this on a more massive scale, then maybe you might want to take a look at some of the CP systems like Bigtable or HBase if you're on the open source side. Many of the systems haven't been proven in production, and there's a consolidation to a smaller number of data stores once the design space exploration settles down. So, so there's like, how would I say? Um, Maybe something like 7, 8 years ago, there was a huge number of new database companies doing NoSQL databases. But now there's less and less of them around. So only a couple of those startups survived, and those systems will stay around while many of the systems will die out just because they couldn't get enough market share in the database side or database market. Now, an interesting thing is that now we're also getting some of these NoSQL systems to implement SQL features. For example, the Google Cloud Spanner is a public release of Google's internal spanner database. It has SQL support. It allows ACID transactions that can span multiple servers globally. So you can do a transaction with different servers on different continents. It is a fully consistent database with a single global database image. So you can actually do snapshots of all the data in Google Spanner, and that snapshot is kind of a global snapshot of all the database tables across all the continents, which is really cool, and it's really good to see. This Cloud Spanner is implemented on top of Paxos for replication. It's also using transaction commits and using atomic clocks uh, based on physical timestamps to figure out which one of the conflicting transactions gets to go first and which one of the conflicting transactions has to wait. In Google Cloud Spanner, all database server clocks are synchronized very tightly using atomic clocks and GPS-based time synchronization across the different data centers. And to keep things kind of externally consistent, then all database transactions have to wait 2 times the max clock drift, holding write locks before committing a transaction. We can take a look at the Cloud Spanner papers if you want to understand how this works on a detailed level. But the basic idea is that if you do a transaction, you basically take locks on all the data you want to modify. And if you manage to take all of those locks, then you take a look at the timestamps at which you took those clocks. And then if you hold then those locks for 2 times the clock uncertainty, then anybody who will grab any one of those locks later on will get the timestamp that is greater than yours timestamp. So your modifications will have priority over or that other transaction. So you will get your transaction committed while the other one will that's concurrently trying to do the modification will actually not be able to commit. Now there are some open source alternatives being developed that use similar ideas. There's CockroachDB and Apache Kudu. These systems are interesting as well. Okay. Okay, so that's kind of now the end of this part of the NoSQL databases or cloud data stores. In future lectures, we'll go through these in more detail. Now, in the rest of the lecture, we'll talk about probabilistic data structures, in particular about Bloom filters. But that's a completely different topic. So if you have any questions, now would be a good time to ask those before we move on to something completely different. Okay, let's move forward. We still have almost, or basically, we have still quite a bit of slides to go, but these we will go through quicker, I'm sure, because we're going through an example. Now, remember that I talked earlier on that the main memory or RAM is a really truly expensive resource in your servers. Because of this, you should use it truly wisely if at all possible. So main memory or RAM memory is much faster than any other form of storage. And because of this, we might want to come up with interesting algorithms that use it very efficiently. And one of the things you can do is to actually use what are called probabilistic data structures and use probabilistic data structures to allow much more efficient main memory usage at the expense of some inaccuracy in the results. And probabilistic data structures are typically used to help things like caching and help things like database indexes to be, or basically to fit larger database indexes into memory. at the expense of maybe some added complexity. Now, the probabilistic data structure I'm going to talk about in this lecture is called Bloom filters. They're an example of probabilistic data structure that's heavily used in several NoSQL databases to minimize I/O using a small RAM-based probabilistic index. And they can also be used for many data analytics tasks to do approximate computations. Um, yeah, it's quite a nice hammer. Bloom filters are also used for many things like they're used quite heavily in, for example, network switches to do various routing related things. Okay, so let's move into it. So what are these things and how can you use them? Okay, so let's take a running example. Let's say we are designing a caching mechanism for a web server. And as input, we're giving a stream of web page URLs, listing each URL that is being accessed. And we want to find those web page URLs that are being accessed more than once to cache them. So the second time you see a particular URL, you put it into your cache. And we do not want to cache any web pages only accessed once, as this can potentially remove more frequently accessed data from the cache. And we allow for a small number of false positives. It's okay to cache a small percentage of items on first access if that speeds up the algorithm, and especially if it lowers the memory requirements they need. So how would you go about doing this? A traditional solution would be to use a hash table. So we'd use a hash table of URLs, and this hash table would store each one of the encountered URLs, cache each URL when it's encountered, and then cache each URL when it's encountered the second time. However, this requires potentially a lot of memory to store the hashed URLs because the URLs are actually quite long quite often, and this can be this can now take a lot of memory per item stored in the hash table. A second traditional design could be to use some kind of an external database to store all the encountered URLs, which would scale beyond main memory hash table, but is potentially slow as each cache access needs to do a database query. So in practice, this is never done. It's caching needs to be super quick, and you don't want to wait for this database query to be done. And now a third design you could do and use a Bloom filter to record the set of encountered URLs, and then use that Bloom filter to figure out whenever you see a URL the second time. Okay. So what are Bloom filters? So Bloom filters are highly memory efficient probabilistic data structures to store sets. And now in the lecture quizzes, you will also have some computations using for Bloom filters that you need to do. The Bloom filter consists of a bit array of m bits. So here I'm using a notation where the bit array is basically an array of bits and is indexed starting from 0. So we have indexes from 0 to m minus 1. And in Bloom filter, the bits are initialized to zeros. Now, to insert a data item in a URL in our case, to this set, what we do is we first compute k independent hash functions, where k is a kind of configuration constant. If you don't know anything, a good default is to use k equals 2 as the first guess, and you will be fine actually in very many different cases. But later on today, we'll see how to compute the optimal number of hash functions for Bloom filter to be as efficient as possible. Okay, so you compute two hash functions based on the key. So you compute some hash function based on a URL we want to add to the Bloom filter. And then let's say k equals 2, then we compute another independent hash function based on that. Um, so, so you basically get two numbers if k equals 2. And these two numbers are then in the range from 0 to m minus 1 to be indexes in this Bloom filter. And now to add a data item to the Bloom filter, what you do is you put the bit at the index position given by the first or 0th hash function, and you put it to 1, and you take a peek at the index given by the second hash function, and you put it to 1 as well. And you do this for all the hash functions you have. But in our case, we just had two hash functions, and that's it. So you basically flip the bits from 0 to 1 for all the indices that you computed a hash value for. So let's take a look at an example. Um, um, so I'll come back to this. I'll come back a few slides back from here from this example. So let's use a Bloom filter of 8 bits of memory, and the bits are 0. Now I use the notation here and also in the quizzes where bit 0 is on the left. Like arrays are written in such a way that the 0th index of the array is on the left and the 7th index of the array is on the right hand side. Now, typical Bloom filter sizes for many applications are in the order of megabytes, if not more. So, but here we use m equals 8 just to fit it on the slide. And as said, we'll use k equals 2. And we compute two independent hash functions, h0 and h1 for this Bloom filter. Um, so that's what we do. So let's add a data item, for example, www.cnn.com to this Bloom filter. What we get is we calculate two hash functions. And then let's say the first hash function returns 2, and the other independent hash function returns the value 5. Then because actually we actually know that because the second or let's say this index here used to be a 0. We know that this hasn't been hasn't been inserted to the Bloom filter, and we can insert the item by setting the second bit, so 0th, 1st, second bit, and the 5th bit, 3rd, 4th, 5th bit to 1. And after the insertion, our Bloom filter looks like this. So we just flip these two indices from 0 to 1, and that's it, Bloom filter after that. Okay, any questions at this point? Okay, let's go back a few slides. Remember, you can ask at any point. So to check whether a data item belongs to the set represented by the Bloom filter, what do? We first similarly check whether two or compute two independent hash functions, and then if the Bloom filter already contains a bit set to all the position, not one position, but all the positions, then what do? We return the data item is potentially in the set. Okay, And now this makes the data structure probabilistic because, okay, if it's a very large Bloom filter, then and we haven't added many items to it, then there's only very few ones in that Bloom filter. Then if we are unlucky and the two positions at which we probe have already a one, then it might be because we've already inserted this item and basically changed both the positions we probe in the case of k equals 2, or it might be that we were super unlucky and there were some other items that happened to change these two positions from 0 to 1, even though our data item hasn't been added there yet. And of course, we can kind of help play the probabilities in such a way that if we make the Bloom filter larger, then basically our probability of having collisions by accident is going down. So the larger the Bloom filter, the less problems there are. So the less probability of having a false positive. Uh, so a scenario where we say, okay, this might be in this set, but it actually wasn't. The probability goes down. The probability of false positives goes down when we add more bits to the Bloom filter. Okay, then consider adding more hash functions. The more hash functions we add, the more positions we probe. So our chances of hitting something by accident in all those positions, of course, goes down. But there's also the other direction. If we use too many hash functions, then adding each element will actually flip more and more bits from 0 to 1. So if we add a lot of hash functions, then each element will flip more and more bits to 1. So if you use too many hash functions, then your Bloom filters will fill in quicker. So there's a trade-off between adding kind of using too few and then getting unlucky because those few positions you probed were actually one, and using too many and getting unlucky because um, your Bloom filter is filling up too quickly, and you would be better off using less hash functions and flipping less bits. So there's an optimal K that you can compute if you know the number of data items you want to add to your filter. But as said, a K equals 2 using two hash functions is a fairly good kind of default. Okay. Now, if at least one of the positions contains a 0, so if in our case we probe either the first position, the hash function 0 position, or hash function 1 position, and there we find a 0 in either one of those, then we know for sure the data item is not in the set, because otherwise we would have set both of those positions. So that's the nice thing. Okay, so after adding, okay, so let's go back. So we had this running example, and after adding the CNN.com, we had this Bloom filter, and we were certain that CNN.com wasn't there because the bit position 2 was 0 before we added this data item D. Then let's suppose we need to add the item www.helsinki.fi, and let's assume that after calculating the k equals 2 hash functions, we get the positions 5 and 0. Then because the before adding this position 0 was bit 0. We know that this is really a new URL. And because of this, we haven't seen this URL before, and we don't need to cache it. Remember, we were doing cache on second access. Then we don't need to cache it. And we just set the bit at the 0th position to 1. And now for the bit at the 5th position, it was already 1, but we keep it as 1 because this is how Bloom filters work. So if you have a kind of collision when you insert stuff, you don't flip that bit. You just keep it as 1. Okay? And now this is the Bloom filter after the insertion. Okay? And then after this, let's say we encounter the www.cnn.com the second time. Now we compute again the hash functions, and of course we get the same numbers as before. We get 2 and 5. Now, looking at the Bloom filter at the position 2, we have 1. At the position 5, we have no 1. Then we actually are correct to notice that this is the second time we see CNN.com, and thus we should cache this web page. And the Bloom filter remains unmodified. So we basically could kind of update this and update that, but those are already ones, so it doesn't change anything. Okay, so we managed to correctly find that this is now seen the second time. Then let's say we add something like www.yle.fi, the Finnish broadcasting company there. Let's say we have the hash functions compute as 0 and 2. And now, because we now have the position 2 already as set as 1, and also the position 0 set as 1, we wrongly assume that this has been added to the set before due to 2 hash collisions. And this is now called a false positive. So we see Yle the first time, and we conclude that it's actually the second time we see it. And thus, in our web caching application, we incorrectly decide to cache the yle.fi already on the first access. And the Bloom filter contents remains the same. Okay, and we already talked about what needs to be done to minimize the number of false positives. But any questions about the running example? Okay, I hope it was clear. Okay, now let's talk a bit more about what needs to be done to minimize the number of false positives. As said, increasing the filter size decreases the number of false positives. However, Bloom filters are usually used when memory needs to be saved. So you might not want to increase your Bloom filters to be really massive. Also, another consideration is that if you have a processor with let's say, or let's say, if you have a massive Bloom filter, then every memory access to the Bloom filter is basically a random memory access. And now your processor might start or want to cache those memory accesses. And if your Bloom filter is very large, it will not fit into the, let's say, level 3 cache of your processor. And that might make your Bloom filter accesses really slow. Okay, that's another consideration. If you make your Bloom filters really massive, your processor cache misses might grow really massive. Okay, then a too small a k, for example, if just using k equals 1, suffers from fairly frequent hash collisions. So if you want to see, this is called so-called birthday paradox, and you can go to Wikipedia and Google up birthday paradox if you haven't heard of it. Thus, avoiding k equals 1 should be done if possible. So basically always, I would say. However, if k is too large, the Bloom filter quickly fills with bits set to 1, as k indexes are assigned to 1 for each inserted data item. And the optimal number k depends both on the memory available and the number of items to be inserted into the Bloom filter. So the less items you need to insert, the more aggressive you can be on the number of the number of hash functions k. And now very large K also slows down processing, as each lookup of a bit of a Bloom filter is a random memory access. And especially if you have a really large Bloom filter, then those memory accesses might be out of the cache of your processor. So that is a consideration as well. So if you make K really large, the Bloom filter becomes really slow. That you don't want to do. Okay, so quickly, kind of the reasoning. Um, what is the probability of a false positive? This is more for you to think about offline if you're interested. I'll just very quickly go through the reasoning. Um, so what's the probability of a false positive? Well, the probability that any bit in the Bloom filter is set to 1 is 1 over m um, or set to 1 by one of the hash functions is 1 over m, because each one of the hash functions sets one of the bits. So 1 over m is the probability when you flip a bit, you flip a particular bit. Then the probability that a particular bit is not set to 1 by any of the k hash functions is then 1 minus the probability of that hash function setting that particular bit to the power of k. Um, so that's, I hope, is understandable. And then if we insert n elements, then the probability that the particular bit b is still 0 is just the previous probability to the power of n. And then you can compute a probability of a false positive, which appears when all the k bits are already set to 1 before inserting an element. Thus, the probability that a bit is already set to 1 to the power of k. So it is the 1 minus this probability, and then that to the power of k. And you can use this formula now to compute the probability of false positives. And if you go to one of the papers that I cite, they then derive that this is roughly the same as this formula here, where E is the Euler's number. So you cannot use either formula basically to compute this. Okay, so that's kind of a quick proof of the false positive probability. Now, how are we doing with time? We're running out of time quickly. Then one of the parameters of the Bloom filter is the optimal number of hash functions. I'm just referring to the paper below, which derives this and says that it's roughly 0.693 times m over n, where m is the size of the Bloom filter and n is the number of items you add. And then in the rest of this, I'll go through this really quickly. You have to go through this for the lecture quizzes. So let's go through a running example. So let's assume that our web caching example We have 10 million unique URLs, and we have a 12 megabyte available for a Bloom filter. What is the optimal number of hash functions to use? And what is the false positive rate for the last inserted URL with this K? And we can just plug in the numbers. So we have 12 times 8 bits times 1024 times 1024 bits. So this many bits, so a bit more than 100 million bits. And we're inserting 10 million items there. And then if we take the formula, 10 million, 100 million divided by 10 million times 0.693, we get roughly 7 hash functions being the optimal for this. And then if we plug in the numbers to the previous formulas for computing the false positives, then we get 0.008, which is 0.8% is the probability of a false positive for the last inserted URL. And then if we do a calculation of what would a traditional hash table take as memory, so let's say that if the hash table entries would take 25 bytes, then having 10 million URLs would take 238 megabytes. And Bloom filter we had was 12 megabytes in size. So by allowing 0.8% false positive rate in caching has reduced the memory requirement by 226 megabytes. So Bloom filters, let's go through this quickly. Then sorry for going a couple of minutes over time. So positives. Bloom filters are a memory-efficient probabilistic data structure for storing sets. Very simple implementation, very fast for a small number of hash functions. They can be combined with a traditional database index. If a Bloom filter says that the data item is not in a database, then a traditional index need not to be traversed. If the Bloom filter says maybe, then we might want to go to a traditional index that might be on a hard disk or an SSD disk. And now Bloom filters also allow for efficient parallelization to create them. So if you need to create a Bloom filter of a really large set, you just compute different subsets of that set on different machines, and then just take the bitwise OR of the Bloom filters created to get the final Bloom filter. And then there are many variants. For example, there are Bloom filters that are so-called stable Bloom filters for stream processing, which start forgetting older items in data stream in a probabilistic fashion. The negatives are there's no delete operations in the basic version, and adding those is difficult. You need to tune K based on the data volume. However, K equals 2 is fairly good. To get very small false positive rates, you need a large number of hash functions, which makes very precise Bloom filters slow. Large Bloom filters are not cache friendly. And if exposed to user-generated data, you may want to run crypto hash functions in Bloom filters to avoid collisions made on purpose by the users. And that might be expensive. And there are even more memory-efficient data structures allowing deletions. For example, there's something called cuckoo filters that is even more memory efficient than Bloom filters, but much more complicated to implement. And here's the pointers to Bloom filters. Okay, thank you for attending today. Remember homework 1 deadline today, and then homework 3 is already out. So see you all on Thursday. Any final questions from anyone? If not, see you all on Thursday. Bye for now.